Okay, now to start the proof, this is what we want to show. So we're going to show that 2 implies 1. So if we have linear combination, if this S is closed under a linear combination of pairs of vectors, then S is a subspace of the vector V. So what we're going to do is we're going to start with the assumption, the hypothesis right here, a non-empty subset of a vector space S. So assume S is a non-empty subset of a vector space V that is closed under the linear combinations of the pairs of vectors. That's 2, right? That's the part 2. Now, what we need to show is that S is a subspace, and so that means we're going to have to show all the conditions. Now, the fact that S is closed under linear combinations of the vectors and that it also inherits the addition and scalar multiplication from V, okay, it'll become obvious that this is closed under those linear combinations, okay? So there are 5 conditions under addition that we're going to check. So first, the closure under addition. So if S1, S2, and S, right? So let's do closure under addition. Okay, if we have S1 and S2, in S, then S1 plus S2 is also in S, as it's a combination of a pair of vectors, and we're assuming that S is closed under those. So that solves that one. That was pretty easy. Second, for any for any S1 and S2 in S, because addition is inherited from V, right? So because the addition properties are inherited by V, the sum of S1 plus S2 in V, right? So the sum of S1 and S2 in S, or excuse me, yeah, in S, right? Also equals the sum S1 plus S2 in V. Right? Because V is a vector space, and because it's a vector space, its addition is commutative. And since it's commutative, well, guess what? Since the operation is commutative, then what? S2 plus S1 is also in V. And that in turn equals the sum S2 and S1 in S. Oh, and all of these are vectors. Keep forgetting my vectors. All of these are vectors. I mean, it's obvious from the context, but and for what I'm saying. Okay, so now, so that means the commutative property holds as well. Now, the argument for the third condition is similar is similar to that of the one we just did. Now, for the fourth one, for the fourth condition, right? So we're going to do scalar. So for the fourth condition, what do we have? We're going to consider the zero vector of V. And note that the closure of S under linear combinations of pairs of vectors gives us this. So if we use the zero vector from V, so if we consider the zero vector in V, right, we could take a pair of vectors, any vectors in S, right? And so we know it's closed under the linear combination of pairs of vectors. So we could say 0 times S1 plus 0 times the vector S2 equals the zero vector, right? So which means the zero vector is also in S. Right? And where S, in fact, actually, we can do that. We don't even need different. Where S is a vector which is any member of the non-empty set S. Now, checking that the zero vector acts under the inherited operations is as the additive identity of S is easy. Okay, so that takes care of that. And now the fifth condition. So the fifth condition is satisfied because for any S in S, closure under a linear combination of pairs of vectors shows that we can get multiplicative, or excuse me, the additive inverse. Right? So because if we take any combination of pairs of vectors, right, under the closure we could show this, right? We could use 0, vector, or excuse me, let's do it this way. 0 times the 0 vector plus -1 times S vector, right? So we take that linear combination there, so, and since it's closed under all linear combinations of pairs of vectors, well, we know that this is an element of S, but this is also equal to what? Negative S, which is an element of S. And it's obviously an additive inverse, right? So now we found the additive inverse of S under the inherited operations. Now the next 5 under scalar multiplication works out similarly. I'm not going to do those here, but I would encourage you to go through all of these and work them out. Okay, now once you prove this implies this, like I said, showing that 1 implies 3 and 3 implies 2 are pretty straightforward. Okay, other than that, have a great day.